Quicksort is an algorithm that uses divide and conquer method to sort a given list of elements. The divide and conquer method basically works on the concept of divide, solve, and then combine. It implies that for a given set of elements, if we apply the quicksort algorithm, the algorithm will first divide the entire array into two parts, and then the individual parts will be again divided into two parts this way. And then finally, when the one list will contain only single element, it will sort it because the single element is already sorted. Then later on, once they divide all the elements in the array into sub arrays and there is no further scope to division, then it combines the result to get the final list of sorted elements. The question here, how does it divide the entire array into two subarrays or elements into two subarrays? Based on the concept used, the divide and conquer methods, we have two divide and conquer methods for sorting. One is merge sort and the other one is quicksort. In this video, we will explore the concept of quicksort algorithm to divide the array into two different subarrays. The quicksort algorithm makes use of a concept of reference value or reference element. At the beginning, when it starts the algorithm, it uses any of the element from the list, any random element, maybe the first element, middle element, or the end element. That reference element is known as a pivot element. Suppose that if we consider the first element and the pivot as pivot element or reference element, then it will try to place this first element 9 in such a way that it will put in the array in such a way that this 9 element placement of 9 elements will divide the array into two subarrays, where all the elements in the left or first subarray with element which is smaller than this pivot, smaller than or equals to pivot, and all the elements in the right or the other subarray, right subarray, will have the elements greater than the pivot. As a matter of fact, the pivot element will divide the array into two subarrays. This is first subarray, this is second subarray. And the pivot element itself will be in its correct position. Once it is been done, this is called the partitioning of algorithm. This is called partitioning. Again, same partitioning, the left subarray will be considered as a new array. Similarly, the second subarray will also be considered as independent new array. Same concept of partitioning the elements into subarray will be carried out here. And again, the subarray, this is a subarray, this is another subarray, and this will be again divided into two subarrays using the same concept used earlier, and then again it will be divided into two subarrays. Similarly, this part also will perform, in this part also the same thing will be performed, and this process continues till we get one element in one subarray. Since there is one element, this element is in sorted order, then we need to combine all the results in the last phase, and that will give you the sorted array. That is the basic concept of the quicksort algorithm, and we'll see the algorithm first. Our purpose of this video is to explore two things. First is the working of the quicksort algorithm, how it works. Number two, to analyze the time complexity. First, we will see how it works with the help of an example. Once we do this working, once we complete this working of the algorithm, we will go for the time complexity analysis. Before we start the discussion of the algorithm, let me again check how it works. First of all, it is a divide and conquer algorithm. That is why it has two steps. One is called divide operation. Second one is the combine operation. And in the divide operation, it partitions the array into two subarrays, as I have already explained, with respect to a reference element. That is, reference element is called pivot element, and such that each element of its first subarray is less than or equal to the pivot, and the elements in the second part of the subarray is greater than the pivot. And computing the pivot is a critical operation to be done in quicksort, and it is done by the partitioning algorithm. Then it conquers by sorting the subarrays individually, and in order to sort that subarrays, we make use of the recursive call to quicksort function. And finally, it combines the subarrays and which are already sorted, so no work need to be done in this phase. And here I'm taking one example. There are 10 elements in the array. Let's say name of the array is A, and the different elements are given in this way, and we will apply the quicksort algorithm in order to sort this list of elements. As said previously, the quicksort algorithm works based on two different algorithms. So one is called the partitioning algorithm, who partitions the entire array into two parts, and then it applies recursively the quicksort algorithm in both the parts. Here, quicksort is the algorithm where A is the name of the array, P is the starting point, the first element here. This is P for this one, and this name of the array is equals to A. R is the position or index of the last element. This is R. Then we will call this partitioning algorithm. We'll call this partitioning algorithm, which is the heart of this quicksort algorithm. That is, it will find the right place for the reference element. It will find the right place for the reference element, and that position will be returned. That Q will hold the position of that reference element. Suppose that we have considered 9 as the reference element, the starting element. Then once we complete one pass, the 9 will be placed in its right position. Let us say at somewhere here, and 11 will go somewhere here. For example, for hypothetically assume that this is the thing, and once we place this, after one iteration, the one element, the first reference element, will be placed in the correct place, and all the elements in the left side will be less than equals to 9, and all the elements in the right hand side will be greater than 9. And once we place this element 9, or the reference element, in its right place, so that will partition the entire array into two parts. Then after that, we will apply the quicksort. Recursively, we will apply the quicksort algorithm in the first half and in the second half. In the first half, now the index here, A will be same, and P will be equals to this element. For this section, it will be equals to 0, and R will be in this case equal to 2. That is, we need to now perform this partitioning algorithm in the first subarray. Similarly, same thing also will be applied to the second subarray, which is denoted by the second quicksort call to the quicksort algorithm in the second time. First time we will call the quicksort algorithm in the first half, and then we will call the partitioning algorithm in the second half. Then that partitioning algorithm once again will divide this one into two halves, and this one will also into two halves based on or with respect to certain reference element that is being taken, that is being considered in order to perform the partitioning algorithm. So here the main part, the heart of this quick sort algorithm, as I have said, that the partitioning algorithm, and the efficiency of this quick sort algorithm depends upon the efficiency of the partitioning algorithm, means how efficiently it can partition the elements, list of elements, into two different sub-arrays. So we will now explain this partitioning algorithm and then we will see how it works. This is the given array A, and this is the partitioning algorithm, and it takes three parameters. One is the name of the array A, then P here, the P is the first index or an index of the first element. In this case, P is 0, this is equals to P, and R is equals to 9, R equals to 9. And now we will start the partitioning algorithm. This is the partitioning algorithm and we'll see how it works. First of all, the statement number 2, we will take one element pivot. We'll take one element pivot as the last element, 6. Because AR is equals to 9 and AR is 6 in this case. Then we will execute the second step number 3, because 1 is only the start. We'll start from step number 2. Then step number 3, we'll take one random variable I, which is equals to P minus 1. P is equals to 0. So I will be, let us take here, I is equals to 0 minus 1, which is equals to minus 1. Basically, it will point, the I will point somewhere here, that outside this array. That's fine for to start with. Then we will use this loop j equals to P. J will take one variable j that points to P. In this case, P is equals to 0. P is equals to, this is P. And then we will continue j less than equals to R minus 1. R is equals to, R minus 1 is equals to 8. So this condition certainly satisfied. So we will go to step number 4.1. If AJ, what is AJ? AJ is equals to 9 less than equals to pivot. Pivot is equals to 6 less than equals to 6. This is not correct. So we will not execute this 4.1.1 and 4.1.2. This is the statement 4.1.2. It is coming in the next line. Then we will repeat this loop. This is the loop from 4.1 and 4.1.2. This is within the loop, for loop. Then we will go to the beginning of the for loop. By that time, j is incremented by 1. So j will point here. Then again, we will check 7. Now we are having 7 is less than 6. That is also not correct. That's why we will not execute the loop. We will increment the value of j. Now j is equals to 5, which is less than 6. This is correct. Once it is correct, then we will execute this loop. As a result of executing this loop, I will increment the value. I will be incremented. It will point to the 0, point to 0, I equals to I plus 1. Then it will execute swap AI. AI is equals to 9 and AJ, j is equals to 5. Now these two elements, 9 and 5, to be swapped. 9, and if I swap 9 and 5, I will have 5 here. I will have 5 here, and I will have 9 here. And by once I do that, I is pointing to 5 now, and j is pointing to 9, and we finish the loop and we'll go to the beginning of the loop again. Then j will come here. Now this j will come to this element 11. Again, we will repeat the same. J is equals to 11. 11 is less than 6, not true. So we'll simply move this j here. Again, 12 less than 6, not true. We'll move j here. Now 2 is less than 2 is less than 6, this is true. If it is true, then we need to first increment the value of I will put I here, I will put I here, then now I and the element I, that is 7 and 2, need to be swapped. So 7 will go here and 2 will come here. So once I do that, I will increment again j to this point, then I will start again the loop 14 less than 6, which is not true, so we will simply move j here. 3 is less than 6 is correct. Once it is correct, I will increment I here. I is pointing to this element. Now I will come here, this is I, so 9 and 3 will be interchanged. 3 will come here and 9 will go there. Once I do this, I will increment the value of j to this place, and I now pointing to this one, this is I. Then again 10 is less than 6 is not correct because pivot is 6. This is not correct. Once if it is not correct, then I will simply increment the value of j, and at this point of time this loop, for loop, will exit because the value of j is equals to 9, which is less than I, less than this one, this condition, less than j is less than r minus 1. R minus 1 is 8, which is not correct. So since it is not correct, so it will exit the loop. So it will exit the loop and it will execute the statement swap ai plus 1. What is I here? I is 9, I plus 1 will be here, I plus 1 means 11. Here 11 and 6 will be interchanged, so 6 will come here and 11 will go there. So the list will look like 5. New list will be 5, 2, 3, 6, 12, 7, 14, 9, 10 and 11. Now this 6 is placed in such a way that in the first half, in this half, in the first half all elements are smaller than 6, and in this part all elements are greater than 6. So as a result of partitioning, the elements are divided with reference to 6, and in the first half all elements are smaller than 6, and in the second part all elements are greater than 6. Then this becomes a new array where p will be equals to 0 and r will be equals to 2. In this half 2, in this half p will be equals to 0, 1, 2, 3, 4 and r will be equals to 9. So now again we will apply quick sort with these two parameters. That is the basic principle of applying the quick sort algorithm, basically the partition algorithm in the quick sort procedure. So this is the status of the array after first pass of the partitioning algorithm. Here these are the original elements 9, 7, 5, 11, 12, 2, and this is the original array. This is the original array. And once we apply the partitioning algorithm for the first time, it is divided into two subarrays, the first subarray and second subarray, where the pivot is being placed in the correct position, and this again being divided into two subarrays. And then we will again apply the partitioning algorithm here. We'll apply the partition, we'll again call the quick sort algorithm in both these partitions independently. Then again we'll go on such way, we'll follow the same way until we get a single element in the one subarray. Once I get single element in all the subarrays, then that single element will definitely be in sorted order. Then we will combine all the results in the last phase of the quick sort algorithm, and that array will give you the sorted element. That is basically the main functioning of the quick sort algorithm. and then we will go for evaluating the time complexity of the algorithm. The partition algorithm is the key component of quicksort algorithm, and as I already mentioned that the efficiency of quicksort algorithm primarily dependent on the partitioning algorithm, because if the partitioning algorithm partitions the entire array efficiently, then the performance of the quicksort is significantly improves. So for to analyze the time complexity, let us first analyze the time complexity of this partition algorithm. Here is step number 2 3 starting from step number 2. The step number 2, it takes 1 unit time to complete this task. Even step number 3 also takes 1 unit time. And step number 4 is a loop who comprises of mainly 2 statements. That's why based on the size of size of the data or value of n, here in this case value of r, considering n equals to r, it takes 2 multiplied by n. This loop executes n times and there are 2 statements. And the statement number 5, it takes again 1 unit time. Step number 6 also takes 1 unit time. Altogether total time required is 4 plus 2 multiplied by n, which is equals to order of n. So partitioning algorithms takes the partition algorithm takes order of n time complexity of the partitioning algorithm is order of n. Now after having the idea of time complexity of the partitioning algorithm, next phase is to see here in this is the array, this is the given array. In the first pass, when we execute this partitioning algorithm for the first time, it divides the entire array into 2 different halves. So first half will have certain number of elements, second half will also have certain number of elements, and one element will be in its correct position. So once it is partitioned, again we need to apply the same partitioning algorithm in this array. Again this will divide into 2 halves, keeping one element at its actual place. This one also will be divided into 2 halves like this, keeping one element in the correct position. So this process continues till we get one element in each of the halves, and then it ends the algorithm. So in order to compute the time complexity of the quicksort algorithm, what we need to do, we need to find the time complexity of the partitioning algorithm in each of these steps. Here there are n number of elements, that's why it takes order of n to partition the entire array. And then the second one, in the second part, in the second phase, in the second pass of the algorithm, this one comprises of n by 2 elements, and this part comprises of n by 2 minus 1 elements. Here I am assuming that the partitioning algorithm divides the array into almost 2 equal halves. And this is the best case. This best case is not always possible to have. So however, we are considering that this is the best case. This is the best case scenario where the partitioning algorithm divides the entire list of elements into almost two equal halves. Considering that scenario, let me compute the time complexity, the base case time complexity for the quick sort algorithm. Considering the base case scenario where every execution of the partitioning algorithm divides the array into two equal halves, the list originally comprises of n elements. That's why the time complexity required for partitioning is order of n. Let me take it as order of n is equal to a constant c and n, cn. Then in the second phase, it will have n by 2 elements in one side and n by 2 minus 1 elements on the other. So it total takes the time to partition these elements. It will take order of n by 2, and this is actually it will take the time c, a constant c multiplied by n by 2, and it has two such partitions, so that's why 2 into c n by 2. Similarly, in the third iteration, it will take 4 into c by 4 into c n by 4, 4 into c into n by 4. Similarly, it goes on up to last, in the last line it will have the n number of elements, total n number of elements. Then n unit time will be taken to in order to perform the last phase, last pass. So altogether, if I sum up all these terms here, then we'll get summation as cn plus 2 into cn by 2 plus 4 into cn by 4 till n, and altogether it gives a time complexity of order of n log n. So this is the time complexity for the best case scenario, best case scenario, best case scenario where the elements are partitioned by the partitioning algorithm into two equals, almost two equal halves. But this is not possible to always get this type of scenario. Mostly the partitioning, when the partitioning algorithm is applied, most of the time it is found that the list of elements are not equally divided into two halves. Rather, it divides in the form such as in one partition out of an element, in one partition either we may have only single element and rest n minus 1 minus 1, that is n minus 2 elements on the other half. Again, when we divide it, one element on this side and n minus 2 minus 2, which is n minus 4 on the other. That way it divides. Or sometimes it may also happen that the elements are partitioned into n elements in one half and 0 elements on the other half, and again this one divided into n minus 1 and 0 and n minus 2. That way it divides. If this type of condition arises due to partitioning algorithm, then this condition is known as the worst case scenario. Worst case scenario. In the worst case scenario, these elements are divided into two halves, where in one half there is no element, and on the other side it has n minus 1 elements. Again, it is divided into similar pattern, 0 element and n minus 3 elements. That way it goes on. So the time required to compute or partition n element is order of n, which is given as constant c into n. In the second pass, it takes c into n minus 1. Third pass, it takes c into n minus 2. If we sum up all the terms, then it gives you cn plus cn minus 1 plus cn minus 2, so on and so forth. And it is equals to actually c into n plus 1 by 2, because it becomes a geometrical series, and that becomes a 1. This is actually 1 n plus n minus 1 plus n minus 2. That way it goes up to 1. So it is actually the time, this sum is equals to n into n plus 1 by 2, and which is nothing but order of n square. So in case of worst case scenario, the time complexity is given as order of n square. This is the worst case time complexity, worst case time complexity of the quick sort algorithm. Or we find the worst case scenario when all the elements either in the ascending order, or descending order, or all elements in the array given array are equal. So these are the three conditions that we can have the worst case scenario, and in that case it will execute this quick sort algorithm will perform with time complexity of order of n square. Apart from the worst case and best case scenario, the quick sort algorithm also come across one condition where the elements are divided into two halves with 1:9 ratio. That is, in one half it comprises of 1/10 of the element, on the other side it comprises of 9/10 of the element. If this is if it happens, then n number of elements in the first pass will be divided into n by 10 elements in the first half and 9n by 10 element in the second half. Again, that 9n by 10 will be divided into two halves where one part will have n by 100 number of elements, and in the second one it will be of 9n by 100. Similarly, the other part also will be divided into two parts as 9n by 100 elements in one side and 81n by 100 elements on the other side. That way it goes on, and this part, this tree, this part or this subarray of the element will be come to one element before the elements which comprises of 9/10 part of the list. So here it ends, this list will end here where we are having only one element, but the other branch or other subarray will still go on, and that way this side will also go on, and finally it will get one element in one sub array, and then it will come to end of the list. And in order to compute the time complexity of this algorithm, either we can add all these terms here, and then we can sum up to order of n log n. So that is the general scenario where the elements are divided into 1:n ratio. And moreover, this calculation can also be done as, say, this is the tree, this binary tree is formed, this tree height of the binary tree is log of n, because there are n number of elements and this is a binary tree. And since every layer, every level of this iteration, we need a time of order of n, that is why n multiplied by log of n, which will be the time complexity in this scenario. So apart from that, there is one more method to calculate the time complexity of this kind of separation or this kind of division, where elements are divided into unbalanced two unequal parts, or either maybe two equal parts, except the worst case condition. When it is divided into such an unbalanced partition, well, we can write down that the time required to sort an array of n elements take order of n plus time complexity 2 into time complexity of 1 by 2, because we are assuming that equally, if the elements of the array is divided equally into two halves, so one part will have n by 2 number of elements. So this n by 2 number of elements again will be divided, this one will be again expanded as 2 into order of n by 2 plus 2 into time required to partition n by 4 elements. And this process goes on. Tn, when it is expressed as order of n plus 2 t of n by 2, it is expressed recursively in terms of tn. Then by applying Master's theorem, this is result into order of n log n. So this is another way to find out the time complexity. So what we have seen here in this time complexity, we have examined the best case scenario where the partitioning algorithm divides the elements of the array into almost two equal halves, and we found out that the time complexity of the best case scenario is order of n log n. We have also seen the worst case scenario where the elements are divided into two halves, where one half comprises of either 0 or 1 element and rest of the elements are placed on the other part. If it happens, then the time complexity is order of n square. It gives the time complexity of all the order of n square. And we found the worst case scenario when all the elements are either in the ascending or descending order, or they have only same number. And third condition also, we have found out that on an average, if it is divided into 1:10 ratio, then also the computation time becomes order of n log n. In both the base case and the average case scenario, this is the maybe considered as average case scenario. In these two cases, the recursive tree grows to a level because every time it is divided into two halves. That's why it leads to a formation of binary tree, and it produces a binary tree with the height is equals to log of n, and each of the level takes order of n time in order to partition that algorithm. That's why total time complexity of the algorithm is considered as or computed as order of n log n.